Horizontal Transformations Part 1. Translations, Reflections, and Even Functions. For any given function, a new function can be created by manipulating the x values arithmetically. The new function is called a horizontal transformation of the original. The graph of the new function will be formed by shifting, reflecting, and/or scaling the graph of the original horizontally. Suppose a function y equals f of x contains the points a f of a, b f of b, and c f of c. We want to locate the points on the function y equals f of x plus h, where h is greater than 0, with the inputs a, b, and c. That is, a f of a plus h, b f of b plus h, and c f of c plus h. We can't do this directly, so we first locate the 3 points on the original graph with those outputs. That is, a plus h, f of a plus h, b plus h, f of b plus h, and c plus h, f of c plus h. Then we find a f of a plus h, b f of b plus h, and c f of c plus h by completing each rectangle. If we do the same for all points in y equals f of x, then we get the new function y equals f of x plus h. We see that the function f has been translated, shifted, or slid h units to the left. The graph of y equals f of x plus h can be sketched quickly by shifting points in the graph of y equals f of x by h units to the left. If h is greater than 0, then to graph y equals f of x plus h, shift the graph of y equals f of x left by h units. To graph y equals f of x minus h, shift the graph of y equals f of x right by h units. These are rigid transformations. That is, the shape of the function does not change. To me, this seems counterintuitive, since replacing x with x plus h makes the graph shift left, whereas replacing x with x minus h makes the graph shift right. Here is a graph of y equals f of x. Can you graph y equals f of x minus 3? I'll give you another second to try it yourself and then show you the answer on the next slide. Note each new value of y was pulled from the left to the right, and so the graph of y equals f of x was shifted 3 units to the right. We'll now move on to horizontal reflections. We start again with 3 points on a function y equals f of x. This time we want to locate the points on the function y equals f of the opposite of x, whose inputs are a, b, and c. That is, a, f of the opposite of a, b, f of the opposite of b, c, f of the opposite of c. We can't do this directly, so we first locate 3 points on the original graph with those outputs. That is, the opposite of a, f of the opposite of a, the opposite of b, f of the opposite of b, and the opposite of c, f of the opposite of c. Now we can find a, f of the opposite of a, b, f of the opposite of b, and c, f of the opposite of c by completing each rectangle. If we do the same for all points in y equals f of x, then we get the new function y equals f of the opposite of x. We see that the graph of y equals f of x has been reflected horizontally across the y-axis to get y equals f of the opposite of x. The graph of y equals f of the opposite of x can be sketched quickly by reflecting points in the graph of y equals f of x horizontally across the y-axis. To graph y equals f of the opposite of x, reflect the graph of y equals f of x horizontally across, over, or in the y-axis. Points on the y-axis, if any, stay in place and are points where the graphs would intersect. We now come to the definition of even functions. If the graphs of y equals f of x and y equals f of the opposite of x are the same, then f is said to be even, and its graph is said to be symmetric with respect to the y-axis. The function y equals f of x below is an example of an even function. Notice that the point a, f of a, is identical to the point a, f of the opposite of a, because f of a and f of the opposite of a are at the same level horizontally. This ends Horizontal Transformations Part 1.